Now we're going to take the concept of Lewis acids and Lewis bases and consider that language in order to consider metal coordination complexes. Okay, so as we discussed, right, we have Lewis bases. We'll donate an electron pair. Whereas a Lewis acid will accept that electron pair. When we're considering metal coordination complexes, we're thinking about the coordination chemistry between a Lewis base and a Lewis acid. So in the same way that, for instance, we discussed the interaction between ammonia and trifluoroborane, where we could say that this could form a Lewis acid-base pair. Another way we can think of that is we can say that this is going to form a coordination complex, or we can even say that the bond that's going to make by the lone pair of ammonia being donated to the acceptor trifluoroboron, right, is what we would call a data bond, okay, or a coordination bond. Okay. And formally, especially in historical literature, this has been notated by showing an arrow, where the arrow is showing that the lone pair of electrons come from the ammonia and are donated to the boron. Okay, and of course this distinction is made. This distinction has been made in the past because this differs from, for instance, a covalent bond, where we define a covalent bond as an electron coming from each of the atoms that participate within that bond. In the case of a data bond or a coordination bond, right, the electrons all come from one of the atoms, right? That is to say, they come from the Lewis base, okay? And that's what we have here. Although often what you will see is that this arrow formalism is not used anymore, and you'll just see a regular line, as you would expect for a covalent bond. But we know from the nature of studying these interactions, right, that this is going to be a coordination bond, that those lone pairs came from ammonia, okay? In a similar way, right, we can think of Lewis acid-base pairs forming coordination bonds with metal complexes, where, for instance, metals, right, would act as the Lewis acid, and then things with lone pairs such as a chloride ion that has lone pairs could act as the Lewis base, right? And so one of the things we can think about is we can look at hexachlororuthenium 4, okay, where this nomenclature is telling us that we have 6 chloroligands, okay, or chloride ions, excuse me, that are going to form bonds with a ruthenium 4 ion, okay? And the way we would draw this is we would have our ruthenium in the central, as the central atom. And there are 6 of these, so this is going to take an octahedral geometry where these are our equatorial atoms. In this case, right, each of the chlorine atoms carries a 1 minus charge. We are saying from the nomenclature here that this is ruthenium 4, okay? So if we have 6 times minus 1, that's a negative 6 charge from the chloro anions, and then a +4 charge from the ruthenium, what we'd have is an overall charge of -2. So we can put this in square brackets and denote the overall charge of the complex as -2. Okay. And sometimes this is shortened where the whole bracket won't be shown. Instead, you just have a corner bracket up here. That's indicating the overall charge of the entire complex, right? Not just the ruthenium atom, okay? And so from here, right, we'll just summarize, right? We call the ruthenium, right, the central atom, right? This is also the Lewis acid, acting as the Lewis acid in the coordination complex. Oops. So, or the metal center. Okay, of the complex, versus each of these chloride anions are acting as Lewis bases, or as we'll more generally refer to them going forward as a ligand. And from here, right, this gives us the vocabulary we need to discuss metal coordination complexes going forward.